Hey, AP Chemsters, this is Mrs. Vanderlei bringing you Blankwalle, Chapter 15, Part 4. This is acid strength and the acid ionization constant called Ka. It's a lot like the K from the previous chapter. It tells us, does it favor the forward or the reverse reaction? And that is all tied in with how strong an acid is, all right? So acid strength is the strength of any electrolyte. In this case, acids will depend on the extent of its dissociation. How far does it break up? That's what that means, into its component ions in a solution. So a strong electrolyte dissolves completely, that's a key word, highlight that word, completely, into ions into a solution. So a strong acid completely ionized, for example, here's one, all right? And what did I tell you to do? Notice the single arrow. Do you remember what we said there earlier? What was the difference between a BCA table and an ice table? A BCA table does what? It goes to completion. There is only a forward reaction and there is no reverse reaction. So is this in a equilibrium way or not? And I wrote, no, it is not. It goes to completion. There is no reverse reaction. All right, well, what about a weak electrolyte? Let's check that one out. So a weak electrolyte will dissociate what? Partially, somewhat, not all of it, into ions in a solution. So our example here, what do we have in this example? We see double arrows. And is this an equilibrium? Yes, it is. Why? There is a forward reaction and a reverse reaction. So some of this will make this. Some of the A minus, remember what we call this? This is the conjugate base. Some of the conjugate base plus the H plus will go back and make your weak acid again. So yes, it is an equilibrium because there are both the forward and the reverse reaction. So let's take a look at what a strong acid is. That's what is up here. So this section is about here, okay? So let me scroll down. All right, so strong acids. There are only 6 strong acids, period. So know them by heart. Why is that such an important thing? Because if it's not a strong acid, then it's a weak acid. All right, so if you will recognize one of the 6 as being strong acid, if it's not, then you have to do something else, okay? So our 6 strong acids are hydrochloric, hydrobromic, hydroiodic, nitric acid, perchloric acid, and the first hydrogen in sulfuric acid, okay? And, you know, why is HF missing? Okay, well, let's go over here. All right, so what can you tell me about the bond strength between the H and the F? It is stronger than HCl, HBr, and HI, so it takes more energy to break the H off than it would in the HCl, HBr, and HI. So it is considered a weak acid. It's a strong weak acid, but it's still considered a weak acid. And what does that mean? Is it a single arrow or a double arrow? Well, if it's a weak acid, it's a double arrow. It's an equilibrium. If it's a strong arrow or strong acid with a single arrow, that means it goes to completion. So that's what this says right here. These 6 acids, when placed in water, will ionize what? 100% all the time. And this means always, okay? So here we go. Here's HCl aqueous placed in water, single arrow, 100% of the time we have H3O plus Cl minus. So this is what it looks like. If I put HCl in the water, what do you notice? I see only ions in here. I don't see any of the original HCl. And here's a molecular version of it. You do not see a single green and white, put together. You only see them separated into their ions. So take a moment out and draw a picture of what happens when HI dissolves in water. So if we start with hydroiodic acid, not just high, but hydroiodic acid, what does the beaker look like? Go ahead and do that. If you did something along these lines, that's what I did. Notice they're all broken up, okay? And so there's no complete molecule HI in the beaker, okay? So hang on, don't turn the page yet. How we started off at the beginning of this section about talking about, equilibrium, K. And I had something about, the K value is a lot like the equilibrium one then from the previous chapter, and the K really shows you, how forward is this reaction. So what do you think the K value of a strong acid is? Think about it. Think about your products over your reactants, okay? What are you going to get? Well, if you think about it, you have all products and no reactants. So if you do the P over R, if you have a big number on top and 0 on the bottom, what does that mean? K is what? K is equal to infinity. That means it is a huge, huge, huge value, okay? So there's no reactants left. Why? Because 100% of the strong acid will always ionize. Will you keep that in the back of your mind? I'd appreciate that. Let's go to the next page. All right, so like I already alluded to, that if it is not one of those 6 strong acids, it's going to be a weak acid. So every other acid that you can think of, all right, is going to be a weak acid. And what does that mean? It does not 100% ionize in water. They will only partially ionize. So it's not a complete. And notice you have a double arrow. So what does this mean? If I put hydrofluoric acid in water, I will make some hydronium ion and some fluoride ion. But what can these two come back and do? Can these two, bump into each other and react and form this again? And the answer is yes, it can. All right, so look at the picture over here. When HF dissolves in water, what happens? What do you see in here? I see some HF, I see some F minus, I see some H3O plus. Notice the original reactant is still in the beaker. Not all of it deionized, all right? Not all of it, there you go, ionized, I should say. Not all of it split up. Or perhaps some of the fluoride and the hydronium bumped together and remade the HF. You will not see that with the HCl. All right, so here's a picture of the HF. So why don't you go ahead and do that for hydrocyanic acid. Take a minute out and draw what that beaker of hydrocyanic acid will look like. All right, this is what I came up with. I have some of them split up, but notice, what did I put right here? Whoopsies, put it back in the beaker. What I put right here, I have the whole hydrocyanic acid is still together in the beaker, okay? So it says the degree of ionization depends on the degree that the acid is weak. So the degree to which a reaction proceeds in the forward direction depends on the strength of the attraction between the H plus and the A minus. So if the attraction between H plus and A minus is weak, then it favors the forward reaction. So what kind of value would that be if it favors a forward reaction? So what did we say in chapter 14? We said that if it is favors the products, it means K is greater than 1, or at least in this chapter, you have a larger value, okay? So what if the attraction between H plus and A minus is strong? All right, that means you're not going to have a lot of products. You're going to favor the reactants. You have mostly reactants left. Then what will it be here? K is less than 1. And for chapter 15, it's going to be a really small value, meaning a larger negative exponent, okay? And something else you need to think about is that the stronger the acid, the weaker the conjugate base. So here's our situation. Remember, we talked about conjugate base earlier in this chapter. So that's the definition of like the Arrhenius definition. Here is we have the H plus, the conjugate base. The HA, lose the H plus, and this is your conjugate base. So here's my acid, here's the conjugate base. So what are they saying? The stronger the acid, you mean that if this is a really, really strong acid, what's it going to do? It's going to mostly go to the forward direction and not so much the reverse action. So what are you going to have more of? You're going to have more of the conjugate base, aren't you? All right. So the stronger the acid, the weaker the base. This base is not going to reclaim an H plus and make more of the HA, are you? What about the vice versa? What if the conjugate base is super duper strong? It's going to grab that H plus and make more HA. What does that mean? Not much of the HA is going to reciprocate and break up again. All right, so the stronger the acid, the more it splits up, the less likely the conjugate base is going to remake the acid. And like I said, the reverse is also true. If it is a weak acid, all right, then the conjugate base can grab the H plus back and not much of the HA will dissociate. Okay, let's go to the next page. All right, so the acid dissociation constant, this is done exactly like what we did in chapter 14. Remember all those times you wrote K equals products over reactants. Remember that? So for any acid, here we go, HA plus H2O makes H hydronium and H plus. And again, H3O plus and H plus are going to be the same thing, okay? I will typically use the H plus because it's a lot easier to write and it's a whole lot easier to type out, okay? So you can maybe rewrite this as HA double arrow H plus A minus, okay? And this is what this is saying over here. So it says, why is the water not included in the Ka expression? Do you remember what we said in chapter 14? Why is water not included? Well, water is a liquid. Liquid and solids are not included in the law of mass action, is it? Okay. So it says the acid dissociation is the same thing as dissolving the acid in water, okay? So, and something else you might want to note, the A stands for acid. So we have a bunch of different Ks, all right? We have the K from chapter 14, which is Kc and Kp. We have Kw, which is a dissociation of water. We have a Ka, which is a dissociation of acids. I bet you could probably guess there's a Kb, which we're going to get to, I think, in 15.7, I believe. And that's going to be the dissociation constant of bases, okay? So it's always good, and I try to model this for you, is to write, you know, this little subscript as to what K are we talking about. There's lots of Ks out there, okay? So let's try problem number 6 here, okay? Let me scroll down. All right, and problem number 6 is, what is the acid dissociation constant for the following generic equation? All right, so they're asking you to solve for what is Ka, okay? Well, what goes on top, everyone? Well, if you said, here we go. Whoops, not that. There we go. The products, remember I said H2O plus and the A minus, they're one of the, or the H2O plus and the H plus are one and the same, so I just rewrote it this way. And the A minus, these are my products over my what? Over my reactants. Do I put water in this? No. All right, and so there we are, okay? So it says, write the sample dissociation reaction omitting water for each of the following acids, then write the acid dissociation expression. All right, so hydrochloric acid. What is hydrochloric acid? What do you know about hydrochloric acid? It's one of the what? Big 6, all right? So what happens? Well, hey, hang on a second. What is the formula for hydrochloric acid? Do you know that? Hopefully you got HCl. So how is it going to split up, all right, into H plus and Cl minus? What is this? This is a what? Single arrow. So if I were to do the Ka, isn't it products over the, how much reactant do I have? I don't have any left. Remember, it's all gone. And what's that going to make? It's going to make infinity, all right? So you remember that? So your Ka is your products over 0, which is infinity. Let's try acetic acid. All right, so if it's acetic acid, what is acetic acid? What's the formula for acetic acid? Remember, I ate something icky. Remember that? So what's acetate? All right, think about that and write down the acid. And this is what I got. Here's my acetic acid. Notice it's a double arrow. Why is it a double arrow? Because it's not one of the big 6, right? So I have the H plus the acetate, okay? And here's my products over my reactant. Notice that this is not 0, correct? Because I still have some left. Will you do me a favor and do chlorous acid all by yourself and see how you do? All right, well, chlorous. Remember, my Sprite is delicious. So what's chlorite? Chlorite was ClO2 negative. So here is my acid, chlorous acid. Double arrow. It's not one of the big 6. Remember, it's perchloric acid. That's one of the big 6, not this one. And it breaks up, and here's your Ka. I think this is a good place to stop. So I'll see you in part 2. All right, don't wait to be great.